The alternating series test, let A sub n be greater than 0 for all n. The alternating series, which can come in two different forms, note you'll have a sign alternator. Then you also have an A sub n term. That's the one we're going to focus on when we do the alternating series test. Now these alternating series will converge when two conditions are met, when the limit as n goes to infinity of your A sub n term is equal to 0. Also, every progressive n value gives you a smaller value, so they're decreasing. First example, determine the convergence or divergence of each infinite series. With our first example, we have the sum from 1 to infinity of negative 1 to the n plus 1 times 1 over n. This A sub n term is the one we're after as far as investigating. So we're going to take the limit as n approaches infinity of 1 over n. That equals 0, so first condition is met. Now, when we slowly increase n by ones, 1 over 1, that's greater than 1 over 2, that's greater than 1 over 3, so condition 2 is met. This infinite series converges by alternating series test. In our next example, we have the sum from 1 to infinity of negative 1 to the n plus 1 over n plus 2. Separating your sign alternator from your A sub n term, we have negative 1 to the n plus 1 times 1 over n plus 2. It's important to keep n plus 2 in the denominator, and we've done that. This is our A sub n term. The limit of that term as n goes to infinity is 0. Fixed numerator, growing denominator, so that's equal to 0. And then if you slowly start putting in 1s, 2s, 3, 4, and so on, you will always get a value that decreases. So this infinite series also converges by alternating series test. And finally, our last example, the sum from 1 to infinity of negative 1 to the n over e to the n. Same case. I pull my sign alternator off, create an A sub n term where I keep e to the n in the denominator. Again, that's important. So 1 over. This is also convergent. We discussed it out loud in class. The limit of this highlighted fraction, as n gets larger, the fraction overall gets smaller. That limit is 0. As you increase n, the values of this fraction keep getting smaller. Let's look at some examples where the conditions may not be met. Again, at the top, this is just a copy paste from the first slide to remind you of how an alternating series looks and the two conditions that need to be met for convergence. Okay, now I'm going to scroll back up and look at these examples. We're going to determine the convergence or divergence of each infinite series. We can tell that we definitely have alternating series. We have a sign alternator term that goes positive, negative, depending on whether we have a odd or even exponent. This A sub n term, its limit is not 0, so condition 1 fails. We don't even really have to check to see whether this decreases. It's most likely not going to be decreasing, but all we need to see is that the limit of this term is not 0. And it's the same case with the second infinite series from 1 to infinity. We have an alternating sign in a series. The A sub n term has a limit of 1, and that's not 0. And we can also go back and think about the divergence theorem. If your limit is not 0, then your infinite series diverges. That was in the divergence theorem. That's probably 2 or 3 videos ago. That would be mentioned in the Series 1 and Series 2 videos that are above in your YouTube playlist. Absolute convergence theorem. If the absolute value of an infinite series, the a sub n term, if it's an absolute value, then we have a series of this format. If the absolute value of your nth term in this infinite series converges, then the series without the absolute value also converges. Definitions. Number one, this infinite series is absolutely convergent when this series converges. The series is conditionally convergent when the series converges without absolute values, but diverges with absolute values. So let's investigate those two types of convergence. First example, we have the infinite series from the sum from 1 to infinity of negative 1 to the n over 3 to the n. Let's wrap this in absolute values, and that's what you see in the pink, absolute value of our a sub n term. Absolute value takes off the sign alternator, because whether you have a positive 1 or a negative 1, the absolute value is always going to be 1. Well, this is a convergent geometric series. So because this series with absolute values converges, we call this series absolutely convergent. The second case would be an example like this number 2. We have the series and the sum from 1 to infinity of negative 1 to the n plus 1 over n. When we put that in absolute value, the sign alternator becomes a 1. Absolute value of n is n. That's a divergent harmonic series. Remember, it has a p or a power of 1. So this is a divergent series. But think back to this beginning one. In the alternating series test, 1 over n has a limit that approaches 0 as n gets large, and it's also full of decreasing terms. So this converges by alternating series test, but when you put absolute values on your a sub n term, you have a divergent. This is called conditionally convergent, only under certain conditions. The second series is called an alternating harmonic series, and it's convergent. With absolute values, it becomes a harmonic series, which is divergent. So hopefully these two examples can help you see the difference between absolutely convergent or conditionally convergent. You can always ask in class or swing by the office if something's not clear.